Hello and good morning to you. You're very welcome to first of our Signpost series here in 2026. We hope you all had a nice break over the Christmas. We have an exciting lineup of speakers for you for 2026. And to start us off this year, we're joined by Eddie Burgess, who's a Teagasc Agricultural Catchment Specialist with the Agricultural Catchments Programme. And Eddie is going to be talking to us about understanding nitrogen loss in agricultural catchments. Good morning, Eddie. You're very welcome to the webinar. You're no stranger to the webinar series.
No, no, probably unfortunately for all your listeners, Mark,
Not at all. No, we always look forward to your presentations, Eddie. And we're joined this morning by Cian Condon, who is the coordinator of the Teagasc Connected Programme. Cian, you're going to be helping us out with questions this morning.
Yeah, that's right. I'm over the Teagasc Connected program. So for anyone who doesn't know, the Connected program aims to get any and all Teagasc knowledge, research, expertise out to professionals in the field right across the sector. So we're just finalising the program for 2026, and if people want to hear about it, I'm sure many of our viewers this morning are signed up to Connected Digital, and if not, they can do so through the Teagasc Connected webpage. So yeah, as normal, people will see on the screen a Q&A function, and we'd be delighted if they'd share their questions, and we'll have a nice bit of time towards the end to put them to Eddie.
Great. Thanks, Cian. So yeah, do use that Q&A tab and we'll have a nice discussion with Eddie afterwards. So Eddie, if you could share your screen with us and we'll hear your presentation, and to remind everyone that today's session is being recorded and will be available on the Teagasc YouTube channel as well as all of the podcast platforms. So you can either watch it or you can listen to it. Perfect. Okay, Eddie, we'll chat to you after the presentation.
Thanks very much, Mark. Well, I know you said I've spoken before, and I'm sure many of your listeners are aware of the program that I work for, the Agricultural Catchments Programme. But for those that aren't, I'll just give a very brief introduction and a couple of acknowledgements. The Agricultural Catchments Programme is funded by the Department of Agriculture, so I'd like to thank those in the nitrates water section of the Department of Agriculture. Currently, Ted Massey is heading up that. Predecessors that we've worked with in the ACP would include Jack Nolan and Bill Callanan, and we're very grateful for their support and direction in the programme. We're funded I'd say really there's three main purposes. We're evaluating measures under the Nitrates Action Programme and the derogation to see are what farmers have been asked to do in the landscape having an impact, or are they very costly and not having an impact? To do that, we undertake catchment science research across 6 catchments. So we have a team of researchers and technical people working in the programme, keeping all the equipment running around the clock and monitoring numerous sites within each of the 6 catchments that were selected to represent different farming systems and soils and different landscapes. But most importantly, we couldn't do this work without the cooperation and support of the little over 300 farmers that manage the land across the 6 catchments. So I'd like to acknowledge all of those. And on the research side of the house, over the catchment science since the start of the programme, Per Eric Melander would be the main person driving the catchment science research in the programme. And I feel a bit like a Swizz sitting here talking to you, because most, if not all, of what I'm going to say is coming out of the research side of the programme and not my work. I'm taking work from the researchers in the programme headed by Per Eric, and a lot of it is Per Eric's work himself that I'm presenting to you. So I just want to acknowledge my colleagues in the programme for that, and thanks very much. So I've been asked to talk this morning about nitrogen loss in catchments, and something I've spoken many times, and some of the slides that I'm going to give here now may be familiar to some of you, but it's not a straightforward, simple thing. And there is an awful lot of focus on nitrate at the moment. And has been, I'd say, for the last 5 or 6 years. Over the course of the catchments programme, I've seen the emphasis switch from phosphorus to nitrogen and back again. But more recently, there seems to be huge focus on nitrogen. And we might ask, why is that the case? Because It's important to be aware water quality is measured by many different parameters, and nitrogen is only one of them. It's not the single factor that determines water quality on its own right. There are many different factors, and we could have very low nitrate concentrations in a particular water body and still have poor water quality. So I think it's important to be aware that it's not the be all and end all. It is important, but it's not everything. Now, why then is there such a focus on this one aspect? Well, the Water Framework Directive runs on a 7-year cycle, and it sets targets for all waters being monitored to be high or good status. And the EPA compile all the monitoring results and put them together every 3 years in a report on the water quality in Ireland, and that came out last year. And they divide water into different types. We've groundwater, and then there's 4 types of surface water: rivers, lakes, what they call transitional water bodies, and then the sea or marine water bodies. Transitional water bodies include estuaries, and they also include lagoons. One that is in the news quite a lot recently is a lagoon is Our Lady's Island. But the vast majority of traditional water bodies are estuaries. And of those 5 different categories, the traditional water bodies are the ones that are poorest and the ones that continue to show the greatest rate of decline. And it is well established, and in the EPA documents, well clearly stated that I have there in brackets, excess nitrogen is the main issue for estuaries and coastal waters, with nitrogen losses being particularly associated with free draining soils in the southeastern half of the country. So if we want to reverse the declining trend in transitional water bodies, and we want to see improvements in that category, it's natural that you would target the nutrient that is considered to be the biggest impact. Hence, we have a focus on nitrogen. In addition to that, we have other environmental factors from nitrogen that we have European regulations on: ammonia emissions, which agriculture is by far the biggest source of ammonia, and we have targets to reach on that, which are not easy, but I think we're just about there. And then the greenhouse gas, nitrous oxide, also comes into is a nitrogen factor. And many of the measures that we'll do to reduce nitrate leach into water will complement other environmental gaseous emissions factors. So hence we have a big focus on nitrogen. I've shown on the top there the diagram of nitrate, the nitrogen being the blue sphere in the middle. Nitrate is NO3, and there's 3 molecules of oxygen and 1 of nitrogen. And it's important, if we're looking at concentrations of nitrate, sometimes they just weigh the nitrogen, and the scale is different. Sometimes they weigh nitrate. So you need to be careful with what units are being used when we're looking at the measurements. Here's a graph from the EPA document showing the 5 different water bodies and the targets. We would like these all to be high and good. And you see rivers, about half of them are, lakes very close to half, coastal water bodies a little over 2/3, but in the estuaries here, it's somewhere between 19% of the water, of the estuarine water bodies reaching the Water Framework Directive status. So that's why we have a target on nitrogen. Now, the EPA report to Brussels every year on the derogation. They report on the nitrogen and phosphorus concentrations in the monitoring sites. And you can see this here is just the rivers. They also include groundwater, lakes, and estuaries. But you can see in the rivers, there is a very clear regional aspect to where nitrate levels are higher. Nitrate N levels are higher in the rivers. And if you drew a diagonal line from Dundalk down to Clonakilty, you could say it's everything, or almost everything, the Wicklow Mountains standing out there in between, but everything on the southeastern side of that line, where nitrate levels tend to be raised. Dilution is one impact of that. We've more rainfall on the western side of the country. excuse me, and that will lower the concentrations. But there are many factors that will cause it. This report goes in for the derogation, and naturally, if you're reporting on the derogation, you would put in a map showing where the majority of the derogation farms are. And you could very simply look at that and say, well, sure, isn't it obvious? The derogation farms are where the nitrate levels are high. But when you delve a little bit further into the situation, you'll notice that this is not the case. Teagasc have, in the last year, launched a campaign, the Better Farming for Water campaign, and they're looking at those catchments that have high nitrate levels. They have 6 catchment coordinators that are looking in detail into the catchments running from the Boyne down to the Bandon and Island, and those that are have higher nitrate levels. And they're looking at the agricultural practice in them. They've spent a fair bit of detail pulling the EPA data and the Department of Agriculture data together. And we can see here the total oxidizable nitrogen, that's nitrate N and nitrite N, so been measured by the EPA. And you can see this is a flow weighted mean. So you could take a time mean, taking a sample every day, but here this is taken into account the volume of water leaving the catchment. And you can see really there are 2 catchments that stand out that have a much higher average nitrate N, or total oxidizable N concentration at 4.3 in the Barrow and in the Slaney. And yet these are the 2 catchments with the lowest organic nitrogen loading going onto them and have the lowest proportion of farms above 170 kilograms organic nitrogen. So not all farms above 170 are in derogation. Some of them are exporting organic manures off their farm. So this is including those that export organic manures to come under the 170 and the derogation farms. So we can see here the catchments with the highest nitrate level of those of concern are the ones with the lowest organic nitrogen loading on them. So if we want to try and reduce this figure, targeting the derogation farms as a source of nitrogen is important, but it's not the whole story. There are other factors that come into play. So what are we doing to mitigate nitrate loss? I often hear it being said that the measures being implemented under the agricultural regulations and incentives are all targeting phosphorus in fresh water and don't target nitrogen loss. And I actually would refute that. I would say that the measures are well balanced and there are many measures in there tackling nitrate loss. I have just listed these off the top of my head. I wouldn't think they're all encompassing. If we look at the regulatory measures in the Good Agricultural Practice regulations, we have stocking rate limits, with chemical nitrogen limits, protein content in concentrate being fed to cows and cattle over 2 years of age at grass, which should lower the nitrogen content in urine while at grass, ploughing dates, targeting mineralization of nitrogen, green cover requirement in stubble ground and over the winter and in ploughed ground. Banding recently came in, so putting your stocking rate based on yield in cows, having a lime requirement in soil sampling, spreading dates for organic manure to match the growing season, storage capacity to give you extra scope over and above the spreading dates if conditions are not suitable for spreading organic manures. Not new ones that have come in recently in the extension of the derogation and nitrogen balance, grazing platform stocking rates tied in with chemical nitrogen and slurry movements. So there's more focus within the farm on individual areas. Buffer margins and additional nitrogen reductions are being applied to 3, I think, of the Barrow, the Slaney, the Nore, I think, I should know this, sorry, but from 2008, where so there's extra regulation coming in there because the nitrates entering the estuaries of those catchments are higher. grass budgeting is something that farmers in derogation and above 170 have been asked to do, all associated with matching the nitrogen supply with the offtakes. Other measures that have been incentivized, straw incorporation, clover and reseeds is a regulation now, multi-species swards, and low emission storage breeding. So there's many measures in place to mitigate nitrogen loss, and many of them have been in place for a long time. And I would wonder what the nitrate levels entering our estuaries would be were these not in place for a long time. So this map here, all this slide here is with details from the EPA. I want to acknowledge the numerous reports, and these are taken from one that came out last August with evidence-based targeting of agricultural measures, and also details on what they call the flag map for identifying pressures being phosphorus, nitrate, or ammonia point source. So the EPA have been monitoring under European Convention, OSPAR, 20 estuaries around the country since 1990, I think it is. And they're monitoring the nitrate levels, entering them, and they've categorized them in this map into the amount of reductions that are required to meet the target environmental concentration of 2.6 of nitrate N. And there is, in recent years, we have seen an improvement. 10 catchments were identified as needing a reduction in the 3-year period, 22 to 24, and they needed an 18% reduction. Sorry, I have these the wrong way around. I should have looked at this. With 10 catchments in 17 to 19, I beg your pardon. From 2017 to 19, 10 catchments needed a reduction. In the more recent period, 3-year period, 22 to 24, 7 catchments needed a reduction of 16%. So we are seeing an improvement, and that is a good news story and something that we need to acknowledge. And that is in part due to those actions that I showed earlier, amongst other reasons. However, if we look at the longer term, and this is also in the report, the lowest levels were identified in the period 2008 to 11, when only 2 catchments of those listed needed reductions. The lowest levels ever identified were in 2008, and the highest levels were in 2016. So there is changes from year to year, and significant changes from year to year. Okay, so we've lots of measures, we've lots of our change in standards. Why is that? Well, if we want to understand the processes that are involved in nitrogen loads entering our estuary and the concentrations in our rivers, we have to have, and it's essential, we have to have at least a basic understanding of the nitrogen cycle. This is a picture from our Ballycanoe catchment where we have a weather station, dairy cows grazing, but I've put in some graphics here. If you can imagine below ground, is below the brown line there in the soil, I'm going to go through the nitrogen cycle. And apologies if this is very basic. This is stuff that I would say is probably done in Leave Insert science, Leave Insert biology, but certainly those that have studied agricultural science would know this, or should know this. There are lots of different pools of nitrogen in the environment. The air contains 78% nitrogen in the form of N2, a very stable form of nitrogen that doesn't move. Soil organic matter contains huge pools of nitrogen. We often hear us talking about building up carbon levels in the soil as a carbon source. Carbon and nitrogen go together in organic matter as hand in glove. And the pair of them equally combine to form organic matter. Both atmospheric nitrogen and N2 and organic matter are very stable and don't change much. But there are many biological processes that will modify a very small proportion, 1 or 2% per year of these, into mineral forms of nitrogen that are available for crop uptake. And crop uptake of nitrogen is needed. The nitrogen needs to be in a mineral form, and plants will take up nitrogen in the form of ammonium NH4 plus, or nitrate NO3 minus. Okay, and these are also forms that are more likely to be lost. So the processes that will add to these, we can have fixation of nitrogen from clover. The bacteria on the roots of clover will fix nitrogen from N2 gas into ammonium and make it available for the clover to grow, or for other crops around it to grow. Bugs in the soil will mineralize organic matter into ammonium, which will further change into nitrate through different bacteria called nitrification. We can apply fertilizer, organic fertilizer or chemical fertilizer, or it can come out of the back end of livestock that are out grazing on the fields. Many different processes happening here, all of which can lead to different levels of mineral nitrogen in the soil. There are also processes that will remove mineral nitrogen. Nitrate could get leached. It can get taken up by plants, as I mentioned. Ammonium will be taken up by plants. In anaerobic conditions where there is a source of carbon and it's reasonably warm, you can have denitrification, which will take the N out of nitrate and release this into the atmosphere. The vast majority going as N2 gas, which is benign and not causing any problem. But along that process, some of it may contribute to nitrous oxide, which is a greenhouse gas. We have immobilization, which is kind of like the reverse of mineralization. So bugs in the soil can convert mineral nitrogen into organic matter. A common example of that is when people plow and incorporate straw into the soil. You're adding a lot of carbon. The bacteria that break down straw being plowed in need a source of nitrogen. They will take mineral nitrogen out of the soil to convert what they're eating, the straw, into organic matter in the soil. So often when you plow in straw, the following crop in the successive year will need, ironically, more nitrogen to make it grow, or would suffer from a lack of nitrogen. Many people are familiar with volatilization of ammonia gas. If you spread urea on warm sunny days, it'll go up into the air. So we now have protected urea, but equally spreading of slurry. At times when it's very sunny, you will have volatilization of ammonia. So there are many different aspects to the nitrogen cycle, and all of these are important if we want to understand how and when nitrate is lost. But at the end of the day, sorry, I'm just going to go back. I'm looking at this leaching section here, and there are two factors that influence the amount of nitrogen leached. One is the amount of water passing through the soil profile. That's excess rainfall over evapotranspiration. If water is not moving down through the soil profile, leaching is not taking place. And there are times of the year when soils dry out and leaching doesn't happen, and then nitrate is not getting lost. And there are times of the year when there's excess water and we've plenty of leaching taking place. When that water is moving, for nitrate leaching to happen, the concentration of nitrate in the soil at that time needs to be higher than the crop requirement. Okay, so if we can break that link, then we're doing an awful lot to reduce the source of nitrogen. Soil type has a huge influence on the amount of water passing through the soil profile. I have a slide here just to give an example. If we had 10 millimeters of rainfall falling into a bucket, it'll fill it up 10 meters. But soil is already half of the capacity is filled with soil, and half of it is in space, either water or air. And if we have 10 millimeters of rainfall falling on a heavy clay soil, if you can imagine this dark grey area being soil moisture that contains nitrogen surplus to crop requirement, and if you imagine the black line at the bottom here being the soil water table, so groundwater levels, if it rains 10 millimeters on a heavy clay soil, it'll push that soil moisture down 20 millimeters. But as the soils get progressively lighter, the same 10 millimeters of rainfall will push the soil moisture down a further depth. And here in the light sandy soil, you can see the soil moisture that contains the nitrate has been pushed down into this water table. and then it can move horizontally, eventually ending up in a spring feeding into a river. And in the catchments, we have two in Wexford that are getting much the same weather. One is predominantly free draining, and it's very evident that in that free draining catchment, the number of water courses is much smaller, because when it rains, the water percolates through the soil. In Ballycanoe, there's a high clay content, and when it rains, a lot of the rainfall flows off the surface, and hence we have a much, much greater density of ditches and open drains carrying the rainfall off into the main channel. The organic loading is higher in Ballycanoe, and the chemical nitrogen rates are higher in Ballycanoe. But ironically, the nitrate concentration leaving the catchment is significantly lower. Again, purely because of the soil type. So if we look at what's leaving the root zone, in Timoleague, we have suction cups and lysimeters in the soil to look at the nitrate concentration actually leaving the root zone. So this is about trying to reduce or studying the source of nitrogen leaving the root zone. And we're comparing 4 different practices. We have one extensively grazed field. We have another grazing platform, another silage ground followed by zero grazing, and another silage ground followed by grazing. And I have 2 years data here. The first year we were only comparing at the low grazing and the grazing platform. And you can see the nitrate concentration leaving and load leaving the grazing platform was significantly higher than in the lowly, the more extensive grazing area. And in the second year, we introduced these other 2 sites. So here we could see that there was very little difference actually between the extensive grazing and the silage ground, but in the grazing platform, the levels of nitrate were higher. So in a pasture-based system, the part of the farm that is most likely to have nitrate loss are the grazing platform areas. And the time that nitrate leaching is likely to happen when water is moving down through the soil would typically be the shoulder periods for the first and last rotation. Now, the next stage, as we move on from soil water into groundwater, we're monitoring in the catchments. We have in a number of our catchments multi-level groundwater wells that we take samples from. So close to the surface, in the deep bedrock, and somewhere halfway in between in the fractured bedrock. And we typically do this in 3 locations: beside the watercourse, halfway up the hill, and at the very top of the hill. And we have groundwater flow in that. So we have this across a variety of soil types. And what we've established is that as the water is moving through the ground, there is processes that will remove nitrogen. And those processes vary massively, both between and within catchments, depending on the texture, soil moisture content, and other physical characteristics of the site. So these transformation processes occur along the way, along what we would call the pathway, from when it leaves the rooting zone to when it enters into surface water. And these are very significant. And they result in a very poor link between the amount of nitrogen that leaves the root zone and what ends up in the stream. So just an example here at the Timoleague catchment, we have 2 sites with 3 boreholes. So we have 6 boreholes altogether. And I'm going to show you results from the borehole closest to the stream in the northern transect. So where I have the pointer there. This is the site. The borehole is over here. The stream is just running underneath those alder trees. And this is the concentration of nitrogen since the start of the programme at the shallowest borehole. It's about 2.5 meters below the ground surface. And we can see 3 peaks that have happened. This was a grassland field and it was reseeded in 2011. And the mineralization of the nitrogen following the ploughing and reseeding resulted in a spike in the nitrate concentration in the shallow well. In 2018, we had a drought, and that also led to a spike in nitrate concentration. And in 2023-24, there was a change of ownership, and the field was taken out of grass and put into tillage. It's been sown maize, beet, and potatoes. And again, we have the mineralization of the organic matter leading to an increase in nitrate concentrations. None of these were an impact of the nitrogen fertilizer or stocking rate load being applied. This is the same site, but at a depth of 18 meters. And we can see as we get deeper, the nitrate concentration is getting lower. And if we go down to 24 meters depth, the nitrate is virtually non-existent. So as you're closer to surface, the nitrate concentration is higher. So this is a schematic diagram that Per Eric very kindly has lent me, and you can see here it's important to identify the pathways that the water is taken before it enters into the stream. Is it overland flow, like in the case of Ballycanoe? Is it close to the surface, or is it coming from deep groundwater? And the colours here are representing the age of the water that's feeding the stream. Is it old groundwater, which typically has very low nitrate levels, or is it quite young, flowing off the surface with runoff, maybe low, but close to the surface would typically have higher levels of nitrogen in it? And at different times of the year, the proportion feeding the stream is going to be different. And I'd ask you to think now, today, I'm in Tullow here in Carlow, and we have had an awful lot of rain over the last week, probably 2 weeks. How much of the water is going to come from old groundwater and how much is coming from either overland flow or close to the surface? In contrast, last summer we had a dry spell and it hadn't rained for weeks. Again, how much is coming from flow close to the surface, or how much is coming from old groundwater? And the answer is it's always a mix, but the proportion of each changes significantly. And actually the proportion of, or the total volume of old water feeding the stream is probably pretty constant throughout the year, but it's the proportion of younger water that goes up and down as soils dry out and wet up. So if I have a schematic here, just if you consider a bottle of water with lower nitrate concentration in it, this is just a single 1 litre bottle, and you're pouring it into an IBC, and the nitrate concentration in the IBC will pick a figure, random figure, 8 milligrams of nitrate N per litre, and we're pouring in a bottle that has 2, because we've done an awful lot of measures to reduce the source of nitrogen. What impact is that the nitrate concentration coming out of the IBC flowing into the stream going to impact the load? So I'm drawing this analogy between the concentration leaving the root zone. What impact does that have on the total volume of water that's in the ground? And when will that impact the load leaving the catchment? Keeping in mind there are processes that happen while it is in the groundwater anyway, and how long does that take? This slide again, to thank Per Eric for, we're looking at the rainfall throughout the year, again in Timoleague, and we can see it's varying monthly rainfall, typically around 80 millimeters, and in October, November and December it was up around 110, 120 millimeters rainfall, but it hasn't varied massively. Here we're looking at the relative proportion of this rainfall that ends up feeding the stream, okay, the runoff coefficient. So in January, February and March, and in November and December, over 80% of this rainfall ends up leaving the stream. But if you look at the months from May to October, when the soils have dried out, less than 40% and closer to 10% in July and August are feeding the stream. The total kilograms of nitrogen leaving the catchment per month vary massively. And in July and August, it's less than 1 kilogram a month. Whereas in the months of November, December and January, we're closer to 6. So nitrate loss is seasonal. That's the load of nitrogen now I'm talking about. How many kilograms per hectare per month leaving the catchment? And what this is telling us is that the closed period for chemical fertilizer and for application of nitrogen makes a lot of sense. And this is replicated across the catchments, across all 6 of them. This table, or this graph, is going back to the very start of the programme, and it's looking at the monthly concentration of nitrogen in leaving the catchment in Timoleague and the annual average concentration. So as we increase the frequency of sampling, we get a lot more information. We know when the load of nitrogen is leaving, and then consequently, we know better how to target our management practices to focus on the periods of the year when the problem is occurring. What is very encouraging is that in 22, we had the lowest nitrogen concentration that we had ever seen up to that point, and 2024 was lower again. So there does seem to be a declining trend in the long term, despite increasing stocking numbers over that period, up to that period. So I mentioned the load there. At our outlet, we have the kiosk measuring the concentration. Every 10 minutes, we take a sample and measure the concentration, but we also measure the flow of the river, that volume of water, which tied in with the previous slide. We do flow gauging, and we correlate that with the depth of water, which has been monitored continuously. And that gives us the total tons of nitrogen leaving the catchment, and if we divide it by the area, we can get the average kilograms of nitrogen per hectare that has been leached per year out of the catchment. I find when I'm talking to farmers groups, this figure means a lot more and makes a lot more sense to them. Typically in Timoleague, it's ranging from around 25 to 45 kilograms per hectare per year. And ideally, we would like to see that closer to 10. So I'm nearly finished here now. We have a challenge really with catchment science, and we often get asked, how well is that measure going to work? For example, if we reduce the chemical nitrogen application rate by 10%, what impact is that going to have on nitrate load leaving the catchments? And there's modelers that work on that to see what impact it is in a given site, in a given situation. But as I have explained, nitrate leaving the root zone is different to what ends up leaving the catchment. So if we're looking at modelling results, we need to be very clear what the parameters are set out that model is working on. And if the model is working on nitrate concentration leaving the root zone, you are taking too big a liberty with that information if you equate that to nitrate entering the estuary. You're taking it one step or many steps maybe beyond the capacity of that model. That's not to say that if the model shows the load leaving the root zone is reduced, it's a good thing. It is a good thing. There is no doubt about that. But there are many other factors and processes that will happen along the way. So linking upstream field scale activities with downstream impacts is really the ultimate objective of what we're trying to do in the Catchments programme. And this involves many sub-disciplines. So we have agronomists, we have meteorologists, we have hydrogeologists, we have ecologists, modelers, and many more. And often across many research organizations, these different disciplines are not connected and not working together. But in catchment science, we try to pull all those together. And we have found that the process rules that we understand from small replicated plot and field scale experiments are very beneficial, but their expected outcomes, which are well understood, are not always evident at a larger catchment scale. And we can't replicate that because at a catchment scale, because catchments are uniquely, they're all unique and they're not replicable. So the approach that we take in catchment science is really to look at high frequency, high resolution time series data. And I'm just going to finish up with the slide of the outlet in the that is replicated across the 6 of the catchments every 10 minutes since 2009. We're measuring total reactive phosphorus, and total oxidizable nitrogen, carbon, turbidity, which equates with sediment, conductivity, temperature, and the discharge, the rate of flow, which gives us a massive data set. And it provides the opportunity to look at different, I suppose, mathematical indices, which can allow us to pinpoint whether the problem is source-driven or mobilization or to do with the delivery. It increases our understanding of the processes, and we don't miss anything that happens. And we can combine it with the lower resolution monitoring that is taking place nationally. And it gives me the opportunity to talk at events like this. Thanks very much. I'll leave it there and take questions.
Thank you, Eddie. Always a really captivating presentation, I have to say. It's you have a great skill in breaking down the science into practical terms. So we really appreciate the time and effort. And look, congratulations to you and the team and the fantastic data that you're able to analyze and present to us here today. I know there's a lot that goes on behind each of those graphs that you're presenting and a lot of work that goes into that. So just to acknowledge that. So Eddie, we've huge interest in this topic. We have over 450 viewers here this morning. So that's a testament to, you must have your own fan base, Eddie, that you're bringing along with you today. But on a more serious note, I mean, nitrogen loss, we talked, you listed out of various measures that are available there. But for the grassland farmers there, bar the limiting of nutrients going out on the farm during those closed periods, is there much more that farmers can do to reduce that end loading during the winter months?
I'd say possibly not, Mark, but there's a huge amount in that. Like we're asking farmers to do an awful lot there. We're asking them to have the necessary storage and over and above the necessary storage. If we have a closed period, which finished last week, but if you have the correct storage capacity, that would have given you the scope to hold off on spreading where conditions inappropriate up until the end of February or maybe early March. Like across the country, we have 16, 18, 20 and 22 week storage capacity. If your tanks and storage facilities were empty when your livestock went in, typically early mid-November, those 16, 18, 20 or 22 week storage should give you the scope to hold on to what you have generated over the winter months up until the end of February, at a time when it goes into it. Budgeting of grass and matching the requirements, the modelling that is coming out of the Grass 10 programme about matching nutrient application rates to growth periods, matching your nitrogen application, all sources of nitrogen application, not just chemical, 2 times of the year when growth is taking place. These are basic, well-established, long-established advice and regulation, and they will and are achieving results. Where I think there is more scope for work and something that hasn't received the same level of attention is on the processes that mitigate nitrate loss along the pathway that I was identifying there, that nitrogen loss is a groundwater, it's not an overland flow pathway, it's a below ground pathway, and we have in Ireland a hugely diverse soil type across the whole country, in contrast to places that have a far greater nitrogen problem like Denmark or the Netherlands, where they have a very uniform free draining soil type typically in the country. Here it's very mixed, And because of the different soil types we have within a field, not to mention within a farm, there are sites that will mitigate nitrogen naturally through denitrification, and cuts in stocking rate and pressure on land from other enterprises like, I don't know, solar panels or forestry, is all this pressure through reduced stocking rates and other sectors looking for it is putting pressure on these wetter areas. And understandably, people are looking to make a livelihood from the land side and from the landscape and the land that they own. And if you're a farmer, you will try and drain that land to get water out of it in order to make it more productive. And that may well have a counterproductive outcome in terms of nitrate loss.
I suppose the point of my question, I guess, was to try and illustrate that it is limited in what you can do to bar the adhering to the closed periods. Now, just linked to that question, there is a question coming through here. Does this point for the need for more stringent measures in nitrogen in leaky catchments? I just wondered what your thoughts might be on that.
Yeah, well, certainly, if we're looking to reduce the nitrate levels, the actions need to be targeted. Whether that's regulation or advice or a combination of both, that probably becomes more a social question rather than biophysical question. But definitely in leakier catchments, in freer draining soils, more needs to be done to mitigate nitrogen loss than would be the case on, for example, the Castlecomer Plateau.
Yeah. Okay, we have a lot of really interesting questions coming through there.
Yeah, there was, I would just say, absolutely run through there. Once Eddie finished, there was an onslaught of questions come in all of a shot. Just understanding the pathways there, Eddie. There's a question here about how will buffer margins mitigate against end loss. Now, there's an additional question there about tree cover, tree planting in those buffer margins, but just as regards understanding the pathways, just that about how buffer margins would mitigate.
Yeah, that's a very good question. And in Denmark, they, I'd say it could be 20 years ago, they brought in massive buffer margins, and they did nothing. And they ended up, and they were regulatory, and they brought them in, and nitrate didn't change at all. And I think they relaxed on that. But it depends what the soil type is in the buffer margin, and it depends what the pathway through that buffer margin is. In the example I gave there, it was on the northern transect in Timoleague. In the other well transect, if I gave you the results of the groundwater well monitoring, the one closest to the stream, even at the shallow borehole, the nitrate levels are virtually nil, because it's an alluvial soil. It has a high clay content and it's prone to getting wet. So if you put a pipe from the higher up the hill slope, where nitrate levels in the groundwater are high, and you pipe it right through that high clay content wetter soil straight out into the watercourse, you've bypassed that damper soil that's more likely to be waterlogged and anaerobic. And if you have a buffer margin there with a pipe going through it, it'll do nothing. But if you have a buffer strip there and the water has to percolate through it, say it's naturally a wetter area beside the river, which often river margins are because the soils are alluvial, you have a higher clay content. And if the water percolates through that, okay, it means that piece of ground is going to get wetter for longer times during the year. But that will increase the rate of denitrification. It is happening in many places. These places exist naturally. And if you look across the countryside, most watercourses, if you follow them along, you will see wet pieces of ground right beside them. And they are doing an awful lot to remove nitrate from soil water before it enters the stream. If we go and remove all those and drain them and put them into grazing paddocks and or silage ground or maize or whatever, and have it draining straight into the river, we have removed that naturally occurring nitrate removal process. So I suppose it depends what you do. Do you bypass the buffer zone with a land drainage pipe, or is it a wet area that water is naturally percolating through? If it's a free draining buffer zone right up to the river's edge and a free draining parent material, I would argue that it's doing absolutely nothing for nitrate.
Okay. Thanks very much, Eddie.
Mark,
you're on. Yeah.
Sorry, I'm muted here. There's a question here, Eddie, in relation to the NLOS in relation to tillage crops and whether spring or winter crops are a better option or have less risk attached to either of those.
Yeah, I suppose regardless of the enterprise, I'm going to come back to the point that I made there that for nitrate leaching to occur, we need two things: water moving through the soil and excess nitrogen above the crop requirement. Okay, so and it depends on what winter crop you have in. If you have winter oilseed rape, for example, it's been sown in the second half of August. It has a massive capacity to take up nitrogen. Typically, on an average year, and the averages can be dangerous, but on an average year, it's taken up a lot of naturally occurring mineralized nitrogen, not applied chemical fertilizer, but nitrogen mineral nitrogen that's naturally in the soil from the mineralization of organic matter. The oilseed rape crop has taken up that before the soils have got wet and before water starts to move down through the soil. And in that case, the tillage crop has done a massively beneficial job. In contrast, if you have a late sown crop of winter wheat going in the middle or end of November, and it doesn't really start to green up until sometime, I don't know, coming above the ground in December, the recharge period that we call when soils get wet and water is moving down and replenishing the water table has occurred before we've had crop uptake. And then we have water moving down through the soil with excess nitrate in the soil above the crop requirement. Okay, and that's one of the reasons why Ireland has received a derogation and why derogation farmers are required to have more than 80% grassland. Grass is considered to be a very efficient utilizer of nitrogen throughout the full year. And even when grass growth rates are low in November, December, and January, there would typically be an uptake of 10 kilograms of mineral nitrogen per month during those seasons. And if we're talking about levels of nitrate loss per year of 30 or 40 kilograms, taking up 10 kilograms a month is very, very significant. But we don't want to add to that by applying any form of nitrogen at the back end of the year, because the soil will naturally supply that itself from the mineralization of organic matter. So emptying your slurry tanks onto grassland in the week coming up to the closed period is adding surplus nitrogen above crop requirement in advance of the time of the year when soils are likely to get wet.
So the importance of really understanding the grass growth curve or those growth curves in your region, I guess, is really important, isn't it?
Yeah.
Question here in relation to farmers' attitudes to these measures, and I know it's maybe not part of your specific research, but I know you have some colleagues working in this area, and so the question is how informed and welcoming are farmers to nitrogen management measures on their farm? Broad enough question, but maybe there's one aspect you'd like to take.
No, I welcome that question. It's a difficult one, and I don't welcome answering it, but I think that's the question that needs to be asked more. I don't know whether I'm fortunate or damned to have been working in the Catchments program since it started. I'd say fortunate. I'm joking aside, I'm very fortunate. I'm really glad to have been here with the program since 2010. I think I started April 2010. I started, so I have a lot of experience, and I honestly believe we have a very good understanding of all the biophysical processes that influence nutrient loss and sediment loss and impacts on ecology. What is a much, much more difficult nut to crack is the socioeconomic behavioral change, why people do what they do, and why they will change what they do. That is the aspect of research and science and advice that I think has most scope for improving the situation environmentally. So farmers' reaction and behavior to it, I can honestly say that the threat to the derogation has done more to increase the focus of farmer behavior on water quality um, um, in the last 3-4 years than I have seen since I started working in the program. The level of interest, so you can see Teagasc Water Quality Campaign, you can see I was at the launch of the Boyne Catchment, and Keepack are playing a major role up there with the beef industry interested. I know Tillage Industry Ireland and the Barrow Catchment, we have the tillage sector interested in it. So ironically, while the derogation has more regulation and more requirement for training, and that the threat to it has really increased farmer engagement. And I would be very concerned that should the derogation go, that level of engagement will not be what it is now.
Yeah, no, it's a fair observation, Eddie. Cian, we have time for one or two last questions.
Yeah, look, just a quick question there is after a dry period, you often have a kind of a real spike in nitrogen loss. Is there anything we can do to alleviate that? Is there any practices on farm that can be done to alleviate that?
Yeah. Well, I think we have learned a lot since 2018. It's the classic example of that. 2018, we had a drought, and across the country we saw very high nitrate levels, and we picked that up in our catchments. The EPA picked it up in their monitoring, and the highest levels of nitrate were seen in 2019. Sorry, I beg your pardon. Matching supply. If we have a shortage of growth and our back is to the wall through an excessively long drought, the reason why growth has been hit is because of a shortage of water. Now, if you're desperate and you don't have feed gone, you will do anything to try and grow more grass. But unfortunately, if forage is not growing because of a shortage of water, applying more nitrogen to it is not going to help. We've learned that lesson, and we now have coming out of the MOST model and the GRASS 10 program delivering that message, very good advice to match nitrogen application rate with predicted grass growth coming down the line. Having said that, applied nitrogen, as I showed in the nitrogen cycle there, is only one source of nitrogen that could end up potentially leaving the root zone. And if we have long dry periods, soils become warm, they open up, they crack, and they become more aerated. And when it does rain, water will percolate through them more freely. The microorganisms in the soil will go into overdrive because they're so warm, and there will be an excessive mineralization of nitrogen, which will get leached, and that will inevitably lead to higher nitrate levels, naturally. On an organic farm, in a forest, anywhere across the landscape, that will lead to nitrate leaching taking place after a drought. To try and reduce that source, I think there's nothing we can do, but I will come back to saying that interceptions along the pathway before it enters into the stream still play a role in that situation.
Yeah. Okay, we're right out of time, Eddie. Huge interest and lots of compliments there on your presentation this morning. So thank you again for that. And that it's just such a fantastic reserve of data that's available there. It's hard to believe that there's nearly 1 million data points for each of those variables. So that's a huge amount of data to work with. So look, Eddie, thanks again for joining us today. Next week we're going to be joined by Dr. Marie Merlo from Teagasc. Is going to be discussing the impact of agricultural diversification on protein security in Ireland. And Eddie, I'd just like to second your view there on that need for more work to be done on the behavioural and socioeconomic piece there around all aspects of sustainable agriculture, be it biodiversity or water quality. So let's hope we can see more resources going into that area. Cian, thanks so much for helping with questions this morning, and we look forward to seeing everybody again at 9:30 next week. So thanks again, and we look forward to seeing you soon.